Hello everybody and welcome to exercise 3 on page 19 of the workbook. Let's read this exercise together. So they're starting us off with a set of 3 vectors, 1, 0, 2, 2, 1, negative 1, and 0, negative 1, 5 in R3. And the first question that they'd like us to answer is, can the vector 1, 1, negative 3 be written as a linear combination of these vectors? Okay, so again, that's like asking us, can we build 1, 1, negative 3 using those 3 vectors as our building blocks? Okay, so algebraically, it's just asking, can we take 1, 1, negative 3 and write it as a linear combination of those 3 vectors that they gave us? Okay, well, if we take that right-hand side and simplify it down a little bit, just add those 3 vectors together, here's what we get. Let's see, a plus 2b plus 0c, and then 0a plus b minus c. Okay, and then finally 2a minus b plus 5c. Okay, and as before, in the previous example that we did, that leads to a system of equations, okay, where first of all the first coordinates have to match each other. So a plus 2b equals 1. Okay, and then the second coordinates have to match each other. B minus c equals 1. Okay, and then finally the third coordinates, negative 3 has to equal 2a minus b plus 5c. Okay, so there's the system of equations that we're trying to solve. We're asking, does that have a solution, or maybe does it have no solution? Okay, and we'll use the approach that we did before of converting that into its matrix form. Okay, so if we did that, it would look like 1, 2, 0, because there's no c, and then 1, 0, 1, negative 1, 1, and then finally 2, negative 1, 5, and negative 3. Okay, now I want to pause for a minute at this point in the problem because this was quite a bit of work. We had to do a lot of writing to get here. There's kind of a nice shortcut, okay, to getting to this matrix that we have here. Do you notice anything special about the columns of the matrix? Notice that the first column, for example, 1, 0, 2, that's the first vector in our set. And the second column, 2, 1, negative 1, that's the second vector in our set, and so on. And then what about the right-hand side over here, 1, 1, negative 3? Well, that's this vector. Okay, so a short way to set up your system is just to take the vectors that are in your set, make those the columns of the coefficient matrix, and the right-hand side is going to be the vector that you're building, that very last column. Okay, and we'll make use of that shortcut in future problems. Now it's up to us to solve this system if we can. Okay, so we'll start by identifying the first pivot position, and we used that term in the last example. A pivot position is just a word for the first non-zero entry in a row. So in the first row, 1 is the first number I can circle that's not 0. And we want to get zeros underneath that pivot position. Okay, so we've already got a 0 right below it. We'd like to get a 0 where that 2 is. Okay, so we need to think about what row operation would do that. And I'm thinking if we take negative 2 times the first row and add it to the third row, we're going to get a 0 in the lower left-hand corner. Okay, so first 2 rows are going to stay the same. Okay, let's just recopy them. And then we're going to take negative 2 times the first row plus the third row. Let's just read it out loud. So negative 2 times 1 plus 2 is 0. Negative 2 times 2 is negative 4 minus 1 is negative 5. And then negative 2 times 0 is 0 plus 5 is 5. Okay, and then finally negative 2 times 1, that's negative 2 minus 3 is a negative 5. Okay, and there's our new third row. Okay, we've got zeros below the first pivot position, and so now let's find the pivot position in the second row. So first non-zero entry in the second row is 1 that I just circled, and we'd like to get zeros below that 1. Okay, so what row operation do we need to make that happen? Well, I'm thinking we'd like to take that 1 and multiply it by a 5 so that when we add it to the 5 below it, we get 0. Okay, so we're going to take 5 times the second row and add it to the third row. Okay, let's get ourselves a little more space here. Okay, and if we do that, let's see, first row is going to stay the same, and the second row is going to stay the same. Okay, and then in the third row, we're going to take 5 times the second row and add it to the third row, so that number is going to stay 0, and then we'll get 5 times 1 plus negative 5 gives us a 0. 5 times negative 1 is negative 5 plus 5 is 0. And then finally, 5 times 1 is 5 minus 5 is 0. Okay, circle our pivot positions and notice we've got zeros below both of those. That's what we want. That's the so-called echelon form. Okay, and so we're ready to think about solutions to this system. Now there's something kind of interesting that happened in this example that didn't happen in the previous one. Okay, focus on the columns of this matrix for just a minute. Okay, in the first column, we have a pivot position that we circled. In the second column, we also have a pivot position. But in the third row, notice that there are no non-zero entries, so there's no pivot position in that third column. And what that means, if you think back to your previous linear algebra courses, that means that C is a free variable because there's no pivot position in that third column. Okay, I'm going to write that down. C is a free variable. Okay, and what that means is that C can have any value that we want it to be. Okay, we can let it be any number that we want. Okay, so thinking back to what we're trying to do in the problem, we want to write 1, 1, negative 3 as a linear combination. That means that we're just looking for any solution to the system, doesn't matter which one. Okay, so since C is a free variable, we're free to give it any value we want. Okay, and, oh, actually, I think we're going to run out of space here, so if you'll indulge me for a minute here, I'm going to sneak that statement in here. C is a free variable, just so we have a little bit more space below. Okay, and since C is a free variable, we can give it any number we want. Let's just choose 0. That's a really nice number. And if we choose C equals 0, what we'd like to do is figure out what A and B are. Okay, so to do that, let's look at our reduced system here. If we write down the second equation, just kind of looking left to right in row 2, we're going to get B minus C equals 1. Okay, and then the first row would read off A plus 2B equals 1. Okay, and we let C be 0, so we'll use that choice for C to see if we can figure out what A and B are. Okay, so starting with this equation, if B minus C is 0, that means that B is C plus 1 if we add the C to both sides, but we chose C to be 0, so we're just going to get 1 for B. Okay, and then move back to this equation. A, if we subtract the 2b from both sides, is 1 minus 2b. We now know that b is equal to 1 from up here. So we'll just substitute that 1 in, and we get, let's see, 1 minus 2 is negative 1. Okay, and so here's what we get. Going way back to the first equation that we started with, we now know that 1, 1, negative 3 can be written as A, which is negative 1 times the first vector, plus B, which is 1 times the second vector, okay, plus C, which we chose to be 0 times the third vector. Okay, I'm going to double check and make sure I wrote that all down right. Looks good. And just make the comment, this is one of many different answers that we could come up with. Okay, because of the fact that our choice for C was totally arbitrary. We could have chosen any other number for C that we wanted to, and we would have gotten another linear combination that would have made this true. Okay, so I think we are done with part A. Let's move on to part B. Okay, so part B asks us, is the vector 1, 0, 1 in span of S? That's like asking you, can you write 1, 0, 1 as a linear combination of these three vectors? Okay, so if we make use of the shortcut that we noticed in part A, that means that we're asking, if we take a system where we take the columns as the vectors in S and take the right-hand side to be 1, 0, 1, we're asking, can we solve that system? Is there a solution to that? Okay, I'm going to ask you to double check my row operations here because they're really analogous to what we just did. So we would start maybe by just recopying the first two rows and then taking negative 2 times R1 plus R3. That gives us the 0, negative 5, 5. Okay, this time we'll get a negative 1 over on the right. And then, recopying the first two rows and noticing, let me circle my pivot positions here. We'd like to get a 0 below that pivot position. We'll take 5 times R2 plus R3, just like we did above. And if we do that, we're going to get 0, 0, negative 1 this time. Okay, there's our echelon form, and the question again that we're asking is, does that system have a solution? Okay, well, if you look carefully at there's a bit of a problem here. And it's the third equation. What does that say if you read it off? It would be saying 0a plus 0b plus 0c equals negative 1. Can that be a true statement? That's impossible, because if you simplify the left-hand side, it says that 0 is equal to negative 1. There's no solution to that. Okay, so here's what we can say, just to bring back a little terminology from maybe a previous linear algebra course. The above system is inconsistent. That's a word that we'll use to say that it has no solution. Has no solution. Okay, and it's because of that last row. The last row reads 0 equals negative 1, which is false. Okay, and so what we can say then is that because that system is impossible to solve, the answer to the question is no. 1, 0, 1 is not in the span of S. It is not possible to write 1, 0, 1 as a linear combination of these vectors. So the answer is no. 1, 0, 1 is not in the span.